is the former software engineer at Butker Institute for Nuclear Physics. No kidding. He's currently the co-founder of Codership. Please welcome Alexey Yurchenko.
Thank you. Well, the title of today's presentation was supposed to be Building Synchronous MySQL Clusters in Cloud and WAN. And it's a very nice topic, and I was quite excited to be delegated to do this. But then there was the agenda, and it literally spells this. And well, this is quite an involved agenda. It will probably take us several hours to cover all this. And most of this is just command lines, and you're probably not here to copy command lines from the screen to your laptop. You probably do more progressive things like copy-paste, which I love. And so I'll try to do what I think a little bit more important and much more high-level presentation. But we will still be quite on topic. And I will start with saying a very dirty word. Does anybody know what word is that? Come on. Who said synchronous? Oh yes. That's the kind of people we want. They are not going to give up and sell for some Santa Claus presents. They will say, they will be naughty. And yes, this word is synchronous. And whatever class you attend to and whatever presentation you listen to, like it may be Herb Sutter on C++, or it can be somebody telling you how to create web pages, or you can be doing some development for OpenStack and Python, and everywhere synchronous is anathema. So why are we going to talk about synchronous today, and what is it good for? If everybody everywhere, like in every textbook, they will tell you that synchronous is bad. And so we'll see how synchronous is bad and why it makes a special sense to make synchronous clusters in wide area networks, which is, as anybody, any professor in the university will tell you that it's impossible, or practically impractical. So let's first recount what is the difference between synchronous and asynchronous applications are on the layman's level. Asynchronous replication means that when you execute transaction on master and then the client sends commit command, master commits the transaction, and then it sends it to slave. And while this transaction is in flight to slave, the master can crash, and slave may never see this transaction, and you get data loss. What is data loss? The client got OK, but there is no record of his transaction anywhere anymore. So there enters synchronous replication, where before you commit transaction locally on master and send OK to slave, you first send this transaction to return OK to client. You first send this transaction to slave and wait for acknowledgement, and then you commit it and send OK to client, and the client knows that if you got OK, then this transaction must be on at least 2 or more servers, and it's redundant. So what we see here is that synchronous replication introduces additional latency as a price for data redundancy. And so this is the first, from here we have the first use case of synchronous replication. It's disaster recovery, which until now most people deal with asynchronous replication. But if we have asynchronous replication and some disaster is happening on your data center one, on the master data center, then there are very good chances that some transactions are lost. And, well, if you care about your data and if you really want to recover after disaster to your complete data state, you want to use synchronous replication for disaster recovery. So this is number one purpose of synchronous replication. It has been recognized decades ago, but well, everybody will tell you that it's impractical to do it over distances of like 30 kilometers or so. Then synchronous replication turns out to have one interesting property, that by the time we need to make a decision whether we commit transaction or not, or whether we can send OK to client or not, we have all required data on our hands to detect transaction conflicts, to resolve the conflicts, and to send a consistent answer to the client. And that opens us a possibility of multi-master clusters where you can write to every node, and if there is a conflict between the nodes, it gets timely resolved, and the client never gets wrong return code. And, oh, sorry. And here you can see that, say, what we are suggesting to return in case of a conflict and rollback transactions. We are returning deadlock error, and it's semantically it's actually quite a deadlock, because we have here two clients trying to modify the same resource, so they're trying to load the same resource, and neither of them can queue for lock. So one of them is aborted, and just like in case of a regular deadlock in a database. So this multi-master was one of primary goals of our goals when we developed Galera, but it's not the primary topic of today. We'll go a little bit further. We'll see how this multi-master capability can help us in wide area networks. So suppose you have some data which needs to be accessed globally. So you have clients in America and in Europe, and you want them to access and modify the same data. And so you have a central server, and clients connect from all over the world. And this is terribly slow, because, say, the latencies between America and Europe are on the order of 100 milliseconds. So the client can send no more than, say, 10 requests per second, which makes it quite unusable. And that's why you have, like, you know, special Facebook site for United States and special Facebook site for Europe and stuff like that, where you have to partition your data geographically. Well, what you want to actually have is something like that. Is that you bring your servers closer to clients and connect those servers synchronously. And you may say that it's pretty much the same thing. Like here we have clients accessing server through like several thousand miles, and now we have like servers communicating between themselves like with great latencies. Well, the thing is that SQL protocol is exceptionally chatty. Well, not so exceptionally, but you usually have to send many requests before you actually do some changes in the database and commit these changes. On average, we see that the replication traffic is an order of magnitude lower than client-server traffic. And so that's why you want to save. You want to save on client-server latencies and pay a little bit, some small price on replication latencies. So, how it looks in numbers. Here I did some simulation. I took two Amazon EC2 accessibility zones, US East and EU West, so one in Virginia and one in Ireland. There are like several thousand miles between them. And they set up two clients and used sysbench benchmarking program to check performance of these clients. And in first case, I connected to a single server located in Virginia, so it was local to American client and remote to European client. And then I tried the same test with the Synchronous cluster with one server located in America and another in Ireland, and clients connecting locally. And here you can see that for local clients, the average transaction execution time was like 30 milliseconds, and for remote client it was almost 2 seconds. So you can see it's kind of 2 orders of magnitude difference. You can say that this server is practically unusable in such situation. It's too slow. But if we use a cluster, then we see that the latencies of both clients, the average transaction execution time, is about 120 milliseconds, and it's about the round trip between those two data centers. And yes, for American clients, the things look not so nice. It takes 4 times longer to execute a transaction. But for European clients, it takes 16 times less to execute a transaction. And so you can see from this graph, this is the average time it takes to execute a transaction, that, well, we kind of have a win here. At least now it is usable globally. And so this is it is this feature of synchronous replication that I'll be focusing on today. Now, before we go any further, a few words about synchronous and semi-synchronous replication. Many people make serious distinction between synchronous and semi-synchronous replication, and especially like professors in the universities, and they will tell you that to be truly synchronous, you cannot just send transaction to a slave. You need to wait for a slave to apply this transaction and then engage in two-phase commit with master and commit this transaction. Otherwise, slave may not be able to apply this transaction, for example. So what? The thing is that it was exactly this academic position of insisting on two-phase commit that made synchronous replication practical, not only in wide area networks, but generally impractical. Let's see what what is the difference between synchronous and semi-synchronous replication in terms of guarantees. Let's consider a small example where we have a master and synchronous replicating to slave, and suppose disaster happens on slave. If we insist on synchronous replication, then we insist on that master stops at this point, because it no longer can get acknowledgements from slave. And you preserve the data redundancy until slave recovery. You don't, data on master is never is always redundant. But we fail availability. And what was the point of adding a slave to our master? It wasn't the point that we lose availability because slave crashes. We don't add slave to master so that master stops when slave crashes, because in this situation we just increase the probability of system failure, because we now have two servers, and therefore there is a 2 times bigger probability that one of them fails, and then we do nothing, because we no longer can do anything synchronously. And if we do a semi-synchronous replication, then okay, slave crashes, and for a while master is alone in the field modifying its database, and these modifications are not redundant, but it keeps on serving your clients. And this is probably what anybody who is doing anything practical with replication will want to have. So, and I must say that Galera is, we often say that Galera is a synchronous replication system, and then people start asking us, and then they say, but it's the same as MySQL semi-sync. But the thing is that, as I'm trying to show here, that this insistence on synchronicity will actually worsen your availability and maybe even worsen your data safety, because the slave may never actually recover. And the master will be staying there. And so the thing is that if you want better redundancy, you just add more slaves, but you don't stop your master because slave dies. So from now on, I will talk about synchronous replication. Well, I will be talking actually about semi-synchronous replication, because that's the only thing that is actually practical. Not only from performance perspective, but also from any other goals that you as database operators want to achieve. Well, we saw that there is the latency. And the latency in synchronous replication becomes ever so more important in wide area networks, because there it is really latency, and you cannot do anything about it because of relativity theory and a limit on information, on the speed of information propagation. And in global networks, the replication latency can reach anything from 100 to 500 milliseconds. So it just takes half a second to replicate a transaction to another node. Well, although if technically, I think with the current state of technology, you can actually go below 200 milliseconds even for fully global network, but realistically it's still kind of 300, 500 milliseconds if you want to go totally global, like Europe, Japan, United States, or it's 100, 150 milliseconds between United States and Europe alone. And that means that a single client cannot do more than a few transactions per second. And this is, even though it's much faster than accessing a global database overseas, it's still kind of very slow. How can we deal with these latencies? Well, the usual way they deal with latencies anywhere. There are two traditional ways, buffering and parallelization. For example, in hardware, there is a huge latency of accessing random RAM from the CPU. So what does it do? It doesn't read a single cell. It reads pages. And so what we can do in our case, instead of auto-commit updates, we group them into multi-statement transactions. The more you can group, the less times you need to replicate, so you win. The more data you can update per unit time. And second, this parallelization, where you, instead of using single client, you use 10 clients. And this is not a wide area network specific thing, because you always use several client threads to MySQL in order to utilize it fully. Simply, again, because of client-server communication latencies. So you will need, if you want to do synchronous clustering wider in one, you will need to maybe sometimes change your application and optimize it for these additional high latencies that I introduced. One way to look at the latency is that synchronous replication ensures consistency between the databases, and if you want to be able to observe both data centers in the same state, you cannot change the state faster than 1 over the latency. If you start changing it faster, then it will be asynchronous replication, and you will no longer be able to see those data centers in the same state, simply because they will no longer act as a single server. Now, so what I was talking before was all kind of general considerations why we want to use synchronous replication in wide area networks. And so far, there is, to my knowledge, only one such system for databases in existence. It's our Galera cluster for MySQL. What we did, we wrote a library that does replication job. And then we wrote a patch for MySQL so it can utilize this library for replication. And other than that, Galera cluster node is a regular MySQL daemon. You connect to it with MySQL clients. You configure it using my.cnf. And then Galera library takes care about synchronous communication with other nodes in the cluster. So it really actually does look like this. You have, say, 3 servers, and then you can connect, you can place them wherever you like on the map, and your clients will connect to these servers, and that's exactly how it is going to work. And there are 3 flavors of Galera cluster. It's what we do in Codership. We take a community edition of MySQL and we write a patch for it, and then guys from Persona and guys from SkySQL, they take this patch and port it to their forks of MySQL. And Galera libraries everywhere is the same. That was our kind of initial starting point. We wanted to write a generic replication library because we believe that replication is replication. It has nothing to do with databases actually, and it doesn't have to know anything about tables or columns or whatever, and as well as database server doesn't have to know anything about replication, like node failures and stuff like that. So we tried to create a clean interface, replication interface for database servers or any other transactional programs. And a very important aspect of Galera is how it fits into CAP theorem. Who knows what CAP theorem is? Well, very few. Well, I'll go in depth a little bit. So, CAP theorem states that in a distributed system, you cannot achieve all 3 properties at once. It's consistency, availability, and partition tolerance. Well, consistency, I guess everybody understands what it is. Availability means that all elements of distributed systems will respond to client requests, and partition tolerance means that they will keep operating as a single distributed system. It won't be broken into multiple parts. So you cannot have all 3 of them. You can have only 2, but normally you can have only 1. And then in case of Galera, it is consistency, of course, because synchronous replication implies consistency. And then you have to choose between availability and partition tolerance. And how you choose that? You change timeouts. The smaller the timeouts, the faster Galera cluster detects node failure, and so the higher is availability of the cluster. Because you don't wait until node comes up and stuff like that. The higher the timeouts, the better is partition tolerance, but the smaller is availability, because it will take longer before you actually decide to expel the node from the cluster. This is kind of an important thing to keep in mind, because very often people want like everything, and especially the availability. And normally you cannot have 100% of availability. There is no such system that will give you 100% of availability with either consistency or partition tolerance. Normally it will be somewhere in between, so the system won't be consistent and it won't be exactly partitionally tolerant. But with the Galera cluster, it boils down to timeouts, and so if something happens to a node in Galera cluster, there will be a timeout before the cluster can continue. That's an important property, and it's very different from asynchronous replication, where you don't care, right? And that's actually one of the fundamental, well, probably most fundamental difference between synchronous replication and asynchronous replication. If you have synchronous replication, synchronous means that you must be synchronous with somebody. So you must know who is somebody. And in asynchronous replication, you just don't care. So you're no longer in a cluster. You no longer have any membership or anything, because you are asynchronous, and the existence of a slave or 2 slaves or 10 slaves is no longer important. So that's the thing, that if you want to maintain consistency, you will have to deal with timeouts. That's kind of fundamental thing. And this is something we need to take into account, because obviously in wide area networks there is far more possibilities of losing connection to a node, and so there may be some hiccups, stuff like that. Well, so if we now try to draw a bottom line to synchronous replication wide area networks and see what we want to achieve here with synchronous replication. First, we want to achieve disaster recovery. I guess many of you have heard that, well, remember that a couple of years ago there were massive outages in Amazon EC2 data centers, like whole data centers were going down, and it took like days for people to recover and stuff like that. So this is one thing. You can always have a disaster in one of your data centers, and you want to be safe. Well, of course, it depends on the data. Then we want to improve performance and service availability by actually improving the access latency to the database by spreading service globally closer to your clients. And let's see what we need to consider when we go into this. First of all, you need to invest in a good link. It's the link in the synchronous cluster. The link becomes the same part of your system as your CPU or IO system or RAM. So, like, if you invest in your nodes, obviously we are making a cluster, so you're going to have not a single server, but a whole bunch of them. Well, invest into a good link. If you are in, say, Amazon Cloud, chances are that they did it for you. Well, actually, links in network in Amazon is quite good for the scale of this operation, and so you can rely on that probably. But if you have some, if you are building your private cluster, you want to use a good link. And the thing is that sometimes people create, there was a real life case that people made 5-node cluster somewhere in Europe and then decided to connect some nodes in, not even Singapore, somewhere from Indonesia to this 5-node European cluster. And, well, nothing good happened out of it because, you know, it's a synchronous cluster, so it goes as slow as your worst link goes. So they didn't, and they did for disaster recovery or something. And if they had just chosen the United States or just another city in Europe, things would be much better. But just adding nodes without much thought can be really detrimental. So, second, categorize your data. There are, like, most likely any big installation deals with many sorts of data. Some data are of global interest, some not. Some data require very fast access, some not, and some are mostly read data. Another, like logs, are most write only, and you almost never read these logs unless you really have to. So, for example, I've been to J-Pipe's presentation and he gave an excellent rundown how they organize their data needs in OpenStack in AT&T. And for example, keystone identity data. If you build your own OpenStack system, you don't want the client to have different credentials in different data centers, right? You want these credentials to be common between all data centers. And this data, incidentally, identity data, is a perfect fit for Galera replication, perfect fit for wide area network synchronous replication, because you don't change it so much often. You kind of say the user changes password, for example. Well, he can wait half a second after he presses the button, right? There is nothing critical about it. On the other hand, they have this oscillometer monitoring tool, which writes enormous amounts of data, and Jay's advice was just use MongoDB for that. And you don't want to replicate it. You don't want this data to be locally available somewhere on the other side of the earth, because it's local monitoring data. It just makes sense only locally. So this is a very important thing to do. Just figure out what you want, what actually needs to be globally replicated. Then, this is the timeouts. And, well, by default, Galera comes with timeouts that are supposed to work good with latencies up to 500 milliseconds. But if you happen to have a network with higher latencies, which is quite rare, but still sometimes there are such things, then you need to properly configure timeouts. I won't dive into details again because it's just mostly copy. Cut and paste you better just use online documentation for that, just a thing to keep in mind. And then with our recent Galera release, we have support for segments. So if you configure segments, then you minimize the amount of traffic that happens between the data centers and save on that. Well, these are things to bear in mind. These are do's. Okay, one more is choosing odd number of nodes and odd number of data centers. Why? Because very often people want to have only 2 data centers or even worse, only 2 nodes. And the thing is that if the link between 2 nodes breaks, then you are guaranteed to have split brain because the nodes don't know if the other one is dead or not. So we have to stop operation here. And actually, a real use case, and this happens quite often, then the link breaks between 2 data centers, but they can still communicate through the 3rd one. And this actually, in real life, it's people saw benefit of it, because this really happened. And then they called us and asked us why it still keeps on working. And we were very happy about it, of course, because it still keeps on working. Now, don'ts. Well, first thing that you don't want to have in a synchronous wide area network cluster is a hotspot. What is a hotspot? It's a table or a row or whatever, some resource that everybody wants to access and modify. And as we saw, there are latencies involved in that. And you cannot modify a single resource, a single row, more often than 1 over RTT, or the biggest latency in the whole cluster. And that means that this thing will go very, very, very slow. And, well, again, it's not wide area network specific, it's just more pronounced in wide area networks. But actually, you will have problems with this kind of database design. You will have problems even on a single standalone server, because there are latencies involved in when 2 threads try to access the same memory area. There are also latencies involved, and you simply won't be able to utilize all CPUs on your system if you decide to go with this design, with a single row. Sometimes they use single row for implementing a counter or something like that. Well, this is not a very good idea. It may be tolerable in case of a single server, but it's not going to work in wide area network cluster. So, poor links. Well, I've already kind of, I started with that you need to have good links, and now it's reiteration of how it is important that you invest in a good link. And, you know, there are good links right now. Nowadays, there are good links. As I already mentioned, when we're talking about synchronicity, we are talking about membership. You always need to know the membership, that you are synchronous with somebody, with not just somebody, but with certain other nodes. And suppose you have a link that loses packets. And it is easy to see that if the link doesn't lose any packets, then it's very easy. We know that the node is together with us. And if it loses 100% of packets, it's also very easy. The node is not with us. There is no link between us and the node. So it's also very easy to detect. But then you can try to interpolate between those 2 extremes, and you realize that somewhere in between you will need to make a totally Boolean decision. This node is or is not a member of a cluster, based on a very fuzzy data. And you know, if you have like 50% packet loss, and you have like 5 nodes, every node will see a totally different picture. Somebody will see, they will see very different membership. And that's the reason why you really want to invest in a good link, because, well, somewhere in between you have a very gray dead area where the cluster won't be able to determine its membership and will be paralyzed. To my knowledge, it happened only 2 times in the field. And I guess that there are like thousands of people who are using it right now in Galera Networks. So it's a rare event, but it's very painful to figure out what is going on and which node is to blame, actually. Then another pain is huge transactions. Huge transactions are bad for many reasons, and huge transactions are bad everywhere. Huge transactions are bad for asynchronous replication just as well. And probably number 2 reason for slave lag. And huge transactions are just bad because they kill all your concurrency. First, you kind of work on this transaction for 2 hours, and then you replicate it, and it takes like 10 minutes to replicate because you are now not in 10 gigabit network, but in Galera network, and then it takes damn long to certify and figure out if there are any conflicts, and then it takes damn long to apply it on a slave. And all this time, master is just sitting and waiting. Well, it's no longer waiting, it's already started to process another transactions, but your slave ends up being very, very far behind. So, the smaller transactions, the smoother is the operation of your standalone server, of your asynchronous replication, and of your synchronous cluster as well. I understand that it's sometimes very convenient to, make huge transactions just because you can, but it's no good, and it may work well with this, well, not well, but it is tolerable with a standalone server, but with any sort of replication, it's really, really very bad, and that's why Perpona, for example, has special tools to, for example, if you want to delete a lot of rows from a table or modify a lot of rows in a table, they have special tools to do it in small increments and keep the operation of the whole system very smooth. And then the last thing is tables without primary keys. It's a very stable tradition that people create tables without primary keys for whatever reason, because say they think that it's a non-important table and we want to save some space and we want to make it simple. And guess what? First of all, if you don't create primary keys, InnoDB will create one for you. And it will take 6 bytes per row. So I'm not saving on disk space or anything. But since by SQL standards those hidden primary keys cannot be exposed anywhere else, then everything else has to operate as if there are no primary keys. And say, if you do this query, delete from 10 million rows table without primary key, on a slave, it will result in that many rows to be scanned. So for every row, for every deleted row, InnoDB will scan this whole table. And on average, it will be like 5 million rows, 10 million times. And that takes days. And that's another reason for slave lag, say, in asynchronous replication as well. So, no primary keys is very bad. Well, now, this was kind of I took a lot of talked a lot about a lot of limitations of synchronous replication on wide area networks, and well, sometimes it just doesn't work for whatever reason, for budget considerations, for some requirements that you need to update certain things very fast and stuff like that. So, if you still want to utilize benefits of synchronous replication locally within the data center, for example, but you kind of need, you can tolerate global latency as well. You always can use Galera cluster together with native asynchronous MySQL replication. You just choose one node in one cluster as master and another node in another cluster as slave, and they will go about their business, and you will have like one big master here and one big slave here. And then if a node crashes, you just reconnect to another node. And if you're using global transaction IDs in MySQL, if you're using MySQL 5.6 or MariaDB, you can use global transaction IDs, and then these changes are very painful, or painless. without it, in 5.5 it's very painful. In 5.6 and MariaDB it's much easier. And now if you use MariaDB, you actually can utilize multi-source replication, and then you don't need to fail over at all, because if one of these nodes dies, well, it just dies and that's it. And you don't care because the rest of the nodes keep on sending data to your slave. But this is asynchronous, and it is no longer a cluster. It's two clusters with a very loose connection. So here I kind of stop and my story, and we go to questions and answers.
Before we start the Q&A, I just want to give a great big round of applause. Thank you, Alexey. First question?
In that chart you had all the way at the beginning, where you showed the how we put the cluster saved. What was the ratio of reads to writes in that sense? Hey, make your homework after.
Are you talking about
Right at the beginning, exactly.
this? Well, is it still on? Okay. Actually, the read-write ratio is a very controversial topic, because, say, if you have a transaction that involves reads and writes, do we consider it like separate reads, or is it reads and writes, or is it a single atomic write, which it actually is? Say, if you do it in a transaction, you cannot, for example, split reads and writes and send writes to one server and reads and writes to another. So you need to consider it as a single atomic write, which involves some reading. This is one thing. Another thing is actually, if you have a select and if you have an update, you can say that the ratio is 1-to-1. But select may take maybe several seconds to execute. and update is an update by primary key, and then it takes just a fraction of a second. So when you say that it's very hard to count.
So to jump ahead, I mean, it seems obvious that the performance gain would be by putting reads closer to the reader, the source of reads. Is there a performance gain that's made by some other mechanism?
No, performance gain here is solely because we have server closer to the client. And it actually doesn't even matter if, well, first of all, Sysbench does, it's an OLTP test. So these are all transactions. So you cannot split them into reads and writes. You have to execute them all. But it doesn't matter so much because I think there are, if I remember correctly, 14 statements and 3 of them are writes. So
every transaction is okay. So there's, I guess my real question is, so there's a performance gain because sending the kind of the remote synchronous update is faster than writing the same distance. Is that correct?
No, the gain here is because it takes much less time for packets to travel between client and server. So when the client select, it takes not 100 milliseconds, but only like 1 millisecond to send select command and 1 millisecond to receive it. And so, in this case, when client is on the other side of the ocean, the time for signal to travel between client and server totally dominates any work that is done by the server. So it's all this time here, like 95% of the time, client and server spend waiting for packets from each other. So, did that answer your question?
Just to be clear, I'm talking about the green shrinking.
Yes, the green shrunk because solely because it took less, because of less time. It takes to send packet from client to server and back.
But doesn't that packet have to get back to the USA?
No. Okay.
Okay, let's move on to the next question. Just to clarify, he will be here for one-on-one questions afterwards, so let's move on to the next one.
Well, Eric, I'm sorry, but that was very important misunderstanding that I want to clear. That yes, the thing is that there are 14 or 15 statements in each Sysbench transaction, and for each statement, the client needs to send statement to server, wait for response from server back, and then send. And so that what takes time. In replication, when we need to replicate data between servers, we need to replicate it only once on commit. So the latency actually, the wide area network latency, the latency between 2 data centers, happens only on commit statement. That's it. That's why we have such a win. I hope now it's clear, right?
Because you have multiple statements that you make before you commit a transaction.
Yes.
And if you're talking for each of those statements across
Yeah,
the
yes,
pond, then aggregate, that's a long time. Whereas if there's a cluster locally, you're making all of those statements, and then when you do that commit, only the one commit is communicating across the pond
Exactly.
to another node. So the latency only occurs one time for that one transaction as opposed to the individual statements that make up the transaction.
Exactly.
Next question? Yes.
Towards the end of the presentation, you mentioned that lack of a primary key will cause a tremendous number of scans on the replication. Is that because does it actually require unique records? Is that what's going on, that it's actually creating a key of the entire record site? And in that case, what do you do if there are duplicate records?
Can I add an extension to that question? And also, why was it exponential?
It wasn't exponential, it was
A lot of
quadratic.
zeros added.
Yeah, it was quadratic. And actually it's,
Scanning for each update, or it's scanning for each?
it scans for each row, and it's actually in the DB property. And that's why people are hesitant. Well, and this is a combination of this in the DB property and Galera using row-based replication, so it transfers the images, not statements, for consistency considerations. And if in the DB doesn't have a primary key, it will scan the whole table for this row. So if you have 10 million rows in a table, and you want to delete them all, as opposed to truncating the table. So you will have 10 million rows in a dataset, and for each row, the table on a slave will be scanned, the row will be deleted, and so on. So on average, the average scan will be 5 million rows, and it will happen 10 million times. And it's a real thing, because sometimes we have, well, not sometimes, but there were several times people were calling us for support and asking what's going on. All our servers are like blocked. Well, they're not locked. They're working very, very hard. They're totally like, they're doing their good job. But, you know, this really, it's quadratic. So even in this case, even like, if you delete 100 rows from such 10 million row table, it can take quite some time.
If I have duplicate records in my master and I delete the first one, what happens on the replication?
Well, it will find, it will scan, and the first row it finds that matches this row will be deleted. But there is no guarantee that it will be in the same physical order on disk or anything. But that's why it's very bad without primary keys, because primary key gives you unique identification of every row and, you know, accountability.
You mentioned for a moment that to use delete as opposed to truncate. How come the optimizer doesn't just use truncate by itself when it recognizes it?
Well, just truncate is not actually a transactional command, from what I understand, and it's a data definition language command. So it's I don't know why it's so.
Right, because you cannot roll back truncates. So let's say if you want to roll back certain things, you can do it for delete, but not for truncates.
Oh, yeah.
Okay. Next question? Yes.
So you mentioned that if you have a low likelihood, it's better for Galera. Do you have like a rough ballpark as to how many writes per second or transactions per second would be best for Galera?
Well,
I mean, it depends on hardware.
no. Well, we're talking about wide area network replication, and there very little depends on hardware. It depends on the distance between the servers.
So do you have like a general benchmark as to, you more than like 10,000 writes per second, and Galera is probably not a good fit?
Well, a single, say if we're talking about replication between America and Europe, single client session won't be able to do more than 10 or maybe 8 commits per second. But if you do it in parallel, well, I personally achieved thousands of commits per second. So it's parallelization allows you to increase the throughput. It's the latencies are high, but you cannot do anything about the latencies. But you can still maintain high throughput. Yeah.
We have time for one more question. Anybody? Yes.
You mentioned one of the techniques to improve efficiency was buffering.
Well, yes, that's like gluing small transactions into bigger transactions. It kind of goes counter to my further statement about that huge transactions are bad. But we're talking now about, instead of auto-commit updates, you make like 10-statement transaction, not a million rows.
But you are committing, at the end of each one, you still are committing. So you're not...
No. If it is a multi-statement transaction, you commit them as a group only at the end when you send the commit statement.
So you're achieving somewhat asynchronous transactions by buffering.
Well, you can say that, and actually you can say that Galera is eventual consistency system because it executes transactions locally without seeing what happens on other nodes. It doesn't take any global logs or anything. But it becomes consistent before it responds to client. So the client doesn't have to deal with like oversold tickets or anything like that. But yes, it's kind of, I guess, it's one property of transactional systems that you're sort of operating a little bit asynchronously. That commits a synchronization points between the client view and the database view.
So to make bigger transactions, you have to train yourself to program like this, or the system takes care of itself?
Well, it's about your application. Does your application use multi-statement transaction, or does it use auto-commit statements? It depends on how application, the MySQL client application, how it is written.
So basically you need to train programmer or database
Yes.
developer.
Yes.
Okay, Alexey will be here for one-on-one questions. I want to give a great big thank you, Alexey Yurchenko.